then. The last thing I'm going to look at is kind of successful use cases for practical applications, and kind of show you some of the examples on what you can use a GAN for today. A lot of this tutorial is going to be kind of my view of the literature around generative adversarial networks, and it's also based on Goodfellow's tutorial that was given in CVPR about 2 years ago. So anybody that's more interested in than what I'm telling you today, you should check out that tutorial. They used the whole day to present kind of different methods to use GANs and different data sets and how you can solve it. Anyways, what we would like to solve with GAN is the task of generative modeling. So we have, usually in machine learning, we have our training data set and a bunch of training examples that defines this. You can call it a distribution. And what we would like to do is model this distribution and just pretty much fit a function on the training data that we have. And if we're able to model the training distribution, we should be able to, first of all, we can sample new images. But we could also evaluate the probability for a certain sample to be existing in our training distribution or the data distribution. And this means that we can use it for kind of outlier detection, for deepfake detection, and other use cases. However, for GANs, we're more interested in the sampling aspect. And this means that we want to train or learn the distribution in our training data. And this enables us to generate new samples that are not present in the training data, but are still realistic. A lot of the GAN theory is inspired by the self-play, which has had a huge success lately, where you just set up 2 machine learning models and then train them against each other. It's been in the machine learning theory for a long time, and it's a very interesting topic, I believe. And kind of DeepMind and OpenAI have shown examples for mastering Go, chess, and then also StarCraft with the idea of self-play. The same success we've seen in GANs, where we went from 2014 and the original paper from Goodfellow, where we were able to model kind of very, very low resolution images. And then we're able now to model full HD and very beautiful images. We've seen the same progress on ImageNet, where we went in 2017, where we were able to model kind of, or we were able to generate images that were recognizable, but really not realistic, until Andrew Burke presented his paper on Big GAN, where they were able to generate really, really astonishing results on the ImageNet dataset for all of the classes. I think I myself found a lot of motivation in GAN theory from just the practical applications that we can use it for. Philip Isola and his colleagues at Berkeley showed this interactive playground, I think 4 years ago, where you could kind of draw doodles and then you could generate an image by yourself. And this was just a web server that you can still access. And then you can also test it out and kind of create examples that it is very not realistic, such as another eye, which shows kind of the ability of GANs to generate images that has never been seen in the training distribution. Going kind of back to the theory from GAN is we're just solving the generative modeling case. And usually when people present this, they categorize it into 2 different categories. So they call it explicit densities and then implicit density functions, where on the one hand you have explicit density, and this, as my understanding of it, is you make certain assumptions about the underlying distribution, which enables you to compute the probability for certain samples and then also compute the density. Examples of this is variational autoencoder and autoregressive models such as PixelRNN. On the other hand, we have GANs and implicit densities, where you don't really make these assumptions, but it enables us to sample from the distribution. And this is kind of the major difference between these two that you should remember from this tutorial, is that with an explicit density function, you're usually able to sample from it, and you're usually able to compute the density function. With GANs, we're just assuming that we're able to sample from our distribution. And the way we're solving this is by defining a generator, which just takes in some random noise, often called a latent variable. And this is random noise, maybe 500 numbers, and then passing this through our model and then generating a sample. The way we're training this, as we don't really have any function to estimate our, to compare our model against the training data, we have to define a discriminator to train it. And this is where this min-max games comes in. You have the generator on the one hand that's trying to generate real samples, and then you have the discriminator, which is just a classification model that is trying to predict, is this image real or is this image fake? The discriminator is usually trained on both the generated samples and then the real data set, while the generator never sees the training data at all. All it learns from is the feedback from the discriminator. And the way it was set up originally by Ian Goodfellow was just maximizing the log likelihood of the output of the discriminator. So you would do one training step for a discriminator and then one training step for the generator, where you would like for the output of the discriminator to be as close to 1 for real data and then as close to 0 for fake data. And then if you train the generator, you would opposite or just reverse this. So you would try to optimize the generator samples to be as close to 1 when you input it to the discriminator. And kind of this basic formulation of a GAN, where you just do maximum log likelihood between the two different distributions, you could generate somewhat realistic images. On the one hand, you have an MNIST dataset that was completely modeled almost, and then the Cypher10 dataset, which is definitely not looking realistic and is very, very poor quality. And this is where I want to focus on for the rest of this talk, is kind of how did we go from these very low resolution images to the images that we're seeing today. And a lot of this talk is going to be about how do we train these networks? So in 2014, neural networks were kind of still a new thing, and it was really hard to just train one deep convolutional network. And then when you played two neural networks against each other, the problem just became way harder. My view of the field which is definitely biased, is kind of, you can separate into the research or the real breakthroughs into two categories of GAN research. And of course, there's a bunch of other contributors here that has enabled us to synthesize as we can. But on the one hand, you have the style GAN papers, which is mostly from Tiro Karas and his team at NVIDIA. And on the other hand, you have the big GAN papers with the recent one from Andrew Brook and his colleagues at Google. And these use quite different tricks to stabilize this neural network training, which I'm going to mention during this talk. And this is kind of where the rest of this presentation is going to focus on. What are the tricks to train these networks? As I mentioned, the hard part of neural net or GAN training is to stabilize them to not just completely collapse. And as Ian Goodfellow said in his tutorial, he said that a lot of the progress in the field has been basic engineering practices or improvements in basic engineering to stabilize the training. And kind of, if you look back at the literature, there's not that many papers that has withstand the test of time which are based on machine learning or basic theory or the questions that we have from the game theory area of research. But I'm going to go through this list. And the first one I'm going to look at is kind of the architecture of GANs. The first paper just used a fully connected neural network, which worked really well for MNIST. And then when they scaled it up to Cypher10, it didn't work at all. They used one convolutional neural network here, or one convolutional layer. And then another work by Alex Radford, they looked at how you could scale up this convolutional neural network. So they found a couple of tricks, such as replacing the relu function with leaky relu, which is just removing the problem of dead relu. And then also techniques such as batch normalization worked quite well. Something to note here is the paper is called Deep Convolutional GAN, even though the model is still only 5 convolutional layers, but they were able to model the Cypher10 dataset quite well. With the original GAN, you didn't have any control on what you were synthesizing. So for example, if you synthesize from the MNIST dataset, you would always get like a random number out. And this is where class conditional GANs came into play, where you wanted to have some control on what you were synthesizing. Mirza presented a GAN where you inputted the class label to the generator as one hot encoded vector, and then also the same label to the discriminator to make both of the models care about the information, and then training them with standard GAN training again. They got quite good results on the MNIST dataset. This was scaled up to the ImageNet dataset by Odina et al. In 2016, where they changed how they were doing it somewhat. So with GAN training, you often have that the discriminator is winning most of the time. So after some time, the training just completely collapses. What they did is they still inputted the class label to the generator, but for the discriminator, they changed it from inputting it and making the discriminator predict it instead. So now the discriminator is a multitask learner, where it learns, first of all, if the image is real or not. And then also it tries to predict what class it originally came from. They scaled it up to ImageNet and it worked quite well. We got recognizable objects in a lot of the different classes for ImageNet, but still they had to train a lot of generators to model the whole data set. They actually trained 1 generator per 10 class, and this means that they had to have 100 generators to model the whole ImageNet data set. Another problem with GANs is kind of how you evaluate it. And this is just underlying from them being implicit density function. If you had an explicit density function, you could estimate the distance between your training data and what your generative model were able to generate. But in GAN training, you would have you see the training data on the left-hand side now, and then the generated outputs on the right-hand side. And you would start with random noise, and then you start to train it. And after some time, you see better results. You see a lot of diversity and better image quality. But if you continue to train this, you might notice that the quality or the diversity decreases while the quality increases. And this is the problem where a generator just figures out that it can focus on a subset of the training distribution and generate this subset really good and not care about the rest of the subset because it's still fooling the discriminator. And it's a problem called mode collapse. And if I continue training this, you would get a complete collapse of the training. Now, for me, if I wanted to use this for a practical application, I would like to know where should I stop training. If I look at my GAN loss function, it's complete garbage, as the loss function just says, how many times did the discriminator predict true for like the fake data versus the real data, which isn't really that informative. And so another problem here is that we are not able to train our model as long as we want. Usually, if you're training out an object detection model, you would get this convergence graph, and you got your minimum point that you always want to stop on, and then you start to overfit. For the GAN case, you train it, and you might get some convergence, and then suddenly it collapses. So it's very hard to choose where to actually stop it. And this was fixed by something known as the discriminator regularization. As I mentioned previously, the discriminator usually wins. And if it always predicts true, or if it always knows if the image is real or fake, the generator never gets any good feedback. and this just completely collapses training. A paper called Wasserstein-GAN looked at that a better discriminator is following a K-Lipschitz function, and this can be constrained in 2 ways. It's called gradient penalties, the one way, where you're just enforcing all the norm of the gradient of the discriminator to be always 1. And on the other hand, you have spectral normalization, which is a weight normalization technique, where you normalize based on the singular values. This is a very brief tutorial, and I'm not going to go into any detail. But what you should remember from this tutorial is that gradient penalties is used by the Stahl-GAN line of research to stabilize the discriminator, while spectral normalization is used by Big GAN. Gradient penalties is really expensive to compute. You have to compute second derivatives, and it takes a lot of time, while spectral normalization is way cheaper, as it's just weight normalization. By using spectral normalization on the AC GAN, they just applied spectral normalization, and now they could train their network for not only 1 day before it collapsed, they actually were able to train it for 20 days. And this enabled us to model the whole ImageNet dataset with a single model and starting to get quite impressive results. And these 4 tricks are kind of what you need to stabilize GAN training or somewhat improve GAN training and improve your final results. And another trick that is very simple to apply that will hugely improve your result is something known as an exponential moving average. It came up in the literature kind of random without any paper on it, but it's the basic idea that when you train your generator, you can have 1 gradient step where the generator is really good, and then you train it for 1 more step, and the stochasticity just makes the generator produce more garbage. This can be stabilized by just making an average of your parameters. So you take a copy of your original generator before training it. So you have this copy, and then for each gradient step on the original generator, you just update the copy. And as you can see in the bottom row, the image quality is way better with this very simple trick. It costs almost no compute, and it has a kind of a small memory footprint. The other thing is noise truncation. When you sample from a GAN, you have to choose between diversity and image quality. And Andrew Burke and his colleagues found out that you can actually control this in some way. So by looking at the noise variable that you're inputting to your network, you can resample, or you can kind of change this some way. And the way they did it is that they defined a threshold. So any value above the threshold is going to be resampled from the normal distribution. And then if you look at the samples here, you can see a threshold of 2, where we have a high diversity of different samples, but a poor image quality on some of them. Well, if we set the threshold close to 0, you get a very high image quality versus less diversity. So this is a way to kind of have a trade-off between diversity and image quality. One thing I'm going to mention very quick is the more theoretical based papers, and that's on what objective we're using to train our GAN. The non-saturating GAN is the original paper that is working quite well still today. And then there's been several papers since then that has looked at different or convergence measures that might be better. Hinge loss is used by the Big GAN paper. I'm not going to mention more about it. Relativistic average GAN is something that came a couple of years ago that changes the task of the discriminator. Usually this discriminator is just predicting if an image is real or fake. Instead, in relativistic average GAN, you predict how real is this sample compared to a random fake sample. And it has shown somewhat of a better convergence. And this is adapted quite a bit in the super resolution community, as I've seen. The last one I'm going to mention is Wasserstein distance. which I'm using currently with my model, and this was used with the original progressive growing of GAN. It was shown to reduce the problem of mode collapse. But something interesting here is the Stahlgren paper that were still first using Wasserstein distance, they actually found non-saturating GAN to work better. So, you know, there's always a lot of choices, and non-saturating GAN seems to work quite well for several papers now. There's a bunch of different tricks that I don't have time to look at. You can send me a message after the presentation if you would like some more information about it. Something interesting to note is that batch normalization isn't always the best to use in a GAN. In fact, Stahlgren found that normalization isn't really needed. I've found the same myself, but they use normalization to apply other techniques other than stabilizing. In the last part of this presentation, I'm going to look at kind of the practical applications that we have GAN and the ability or different modeling abilities that we have. The first one I'm going to look at is the Stahlgren paper. They showed a very cool feature where they are able to change the content of an image without changing the style. And here style can refer to such as the hair color or the color of the eye. And this is called disentangling style and content. And I'm going to show you right after. You can see that they're able to change the style of an image while keeping the content of it. And the way this is done is that a lot of the content information is found in the spatial relationships between pixels, while the style is often embedded in the feature maps from a convolution. So each activation has, or the variance between different feature maps in the same activation might say something about the style. So you can change the style by just multiplying each feature map with different values, and you can learn this multiplication constant, which they show here. Another thing you can do with Stahlgren is projection, where you can go from a target image and then invert the generator. So pretty much just finding the noise vector, which produces this image. With a properly trained generator, you're able to do this perfectly with fake samples, but with real samples, you're not actually able to invert it perfectly. So on the right-hand side here, you can see real images, which is tried to project. And you can notice that the image is similar, but it's not completely identical. And this could be used for checking if an image is generated or not, or at least the authors argue for that. Another cool application is image-to-image translation, where you can go from like one domain, such as grayscale, and then go to RGB images. And this is the work of Philip Isola, I believe 4 years ago. And there's a really cool interactive demo that you can check out today by Håkon and Mingyu Li and his colleagues, where you can define a semantic map. So just saying this area should be sky and this area should be sea. And then I tried to draw a crooked bridge, and it generates something that looks realistic. In the same paper, they show the ability to change the style without changing the content. So you can see kind of the midnight sun and then also sunset. So this is the same method as Stahlgren is doing, to just change the feature map activations, which is pretty cool. In the same paper, they show an interactive demo that they have, where you could kind of do interactive editing. And this can be used for some very cool artistic work, such as quick drafting of scenes or different abilities. One of the most popular GAN repositories on GitHub is called Zeoldify, where you go do the task of colorization, where they go from one grayscale image to a color image. And they also apply this for videos. And a really cool thing about this is that this is an image-to-image model, and they're not doing any modeling of the temporal consistency. They're also doing some funny stuff to actually train this, and they're calling their method no GAN. And this means that they're training the generator on something known as perceptual losses first. And then they're training their discriminator while keeping their generator static, and training this discriminator till convergence on generated samples and real samples. And then they do like 30 minutes of GAN training, and they get these results. What I work on is the task of image impairing, where you have certain images or certain areas of an image that is corrupted, and then you might want to fill it out. And this paper from ICCV last time showed an image impairing model that was able to have user input. So you see on the right-hand side or right top corner, you see that you can kind of draw user input. In our case, we use image impairing for face anonymization, where we, instead of kind of doing standard blurring of images, we want to use a GAN to generate new faces. So in this way, we can try to anonymize all the individuals in a movie with just using a GAN. So here we're doing object detection, key point estimation, and then putting a GAN on top of it. This is built by just having an image impairing model where we have the original face and we remove certain parts of the image. And then we try to generate, or we put it through the generator with some noise variable, and then we are able to generate a new image. And then this is trained with pure GAN training. Our model is able to generate different personalities for the same person. And here I'm using the truncation value trick, where you can kind of change between diversity and image quality. And we can also input the pose information to the model, and then change how the output is going to look. All my work is open source, and I hope that you might take a look at it. And that's going to be the end of my quick introduction to GANs, and I'm happy to answer any questions that you might have. Thank you.